So I wanted to start with a little reminder of some of the things we talked about the last time. So the job of the lecture yesterday was to compute this expectation value, which is the expectation value in the future of the gravitational waveform set up in some scattering event. Now this form here is the form after using the stationary phase approximation. So there's a 1 over 4 pi r, some factor of minus I, just a frequency integral left to be done. The quantity or this wave shape, I've just written well, I have in mind the leading order wave shape here. So the 5.3 amplitude is sitting inside this alpha here, and some points of notation which are important is that the k, the momentum of the gravitons, is evaluated at the frequency that's in this integral here times this vector n. So the vector n is a null vector pointing from the source of the gravitational waves at a retarded time to the observer at some coordinates x. Now, I mentioned yesterday that the expectation value of this h mu nu operator in the far past is 0. So the initial expectation is 0. Okay, well, that's just the way it works out in this calculation. Now, thinking about the same kind of computation, the same physics using classical methods, one thing we could just do is only take two particles, two objects in the far past that are gravitating, and scatter them off one another. Well, then in the far past, the metric deviation will be given by some formula, for example. So, say classically, maybe it's worth saying a couple words. So in the far past, the two bodies that we're scattering are very far apart. So even if we're doing, classically, I mean, in this whole story, we're performing full nonlinear general relativity, order by order, and perturbation theory. But when the objects are very, very far apart in the past, the metric will linearize. So the total metric in the far past will be the sum of contributions of each body. The two objects we're scattering they're very far apart. So we can use linearized GR. So the metric in the far past is going to be the sum. Linear combination, just a linear sum. It's the sum of the contributions from each object. Now, I'm making this point because, since the situation is linearized, I might as well just talk about the contribution of an individual black hole. And for most of today's lecture, I'm going to be focusing on contributions of an individual black hole, with the understanding that if I want to scatter some bunch of black holes, 2 or more, well, then we just add them, right? Well, very good. So now, what are these contributions? I have to pick a gauge. Right? So, e.g., one obvious gauge to set up a perturbative computation is the Donal gauge. Well, in the Donal gauge, the metric deviation is let's just write it here. So I'll write h mu nu dd for the Donal. Well, the formula is minus 4gm. I'm going to put a capital R here times the relevant projector, v mu minus e to the mu. Okay, so the R here is the spatial distance between where the black hole is and whatever the position x in the rest frame. Now the v mu would be the proper velocity for velocity of the black hole. I'm using notation v mu today. I've been using little u for velocities in the past lectures. Today I want to switch to v, and it's mainly because this u here is a very standard symbol for the retarded time. So u is t minus r, the retarded time, and well, I wanted to avoid confusion with that little u, so I'm switching to v for the velocities of the black holes for this lecture. Okay, so that means in particular that this r, well, r squared then will be v dot x squared minus x squared. So the job of the v dot x is to cancel the time components in the x squared. All that's left are the spatial components in the rest. Whereas the minus sign is just a bug of the mostly negative metric convention. Okay, well, a first comment about this is it's not zero. I mean, obviously it's not zero. So you might wonder, how on earth is that consistent with this expression here? And that's really the topic of the lecture today. You might think it's very strange. I certainly thought it was very strange. When I was learning quantum field theory, that you have these objects, charges, black holes, whatever they are. I create a point particle state, and then I look at what the field, the metric, or the photons. The same comments will apply for photons. Just seems a bit strange as you get nothing out of it, right? So I want to explain how that all works. So it all makes sense in the end, but there's a bit of a story to it. Now, so this thing's obviously non-zero, but at least I'm going to make sort of two qualifications about comparing these things. But one first qualification is that this thing is non-zero, but it's definitely gauge dependent. All these, this is metric, as I said yesterday, it's gauge dependent, it's going to have some gauge transformation. So I want to spend a little bit of time discussing the kind of gauge transformations that are relevant in this context. And that really brings us to the topic of the lecture. Yeah. Yeah, so V is dimensionless. Yeah, V is a proper velocity, so you think of it as 1, 0, 0, 0. In its rest frame, it's just 1. Yeah, so yeah. Yeah, that's right. I've lined that black hole up in the origin. Yeah, I mean, yeah, this is x squared plus y squared plus z squared. That's true. So I may be being a little bit evil because I'm telling you that if you've got multiple black holes, you just have to add them up. Of course, then you need to translate one with respect to the other, so it'll have some parameter in there. Okay, so I wanted to spend a couple of minutes just discussing how to think about the gauge transformations of these objects, just classically. So now this is the topic of asymptotic symmetry transformations, or the BMS group. It's the main topic of our lecture today. BMS. Okay, now we're interested in a situation where we have an observer, like our position x, which is very, very far away from some event. So the gauge transformations I'm going to be interested in are gauge transformations that do not go to 0 at large distances. These are known as large gauge transformations. So our observer is from the source. And this, this very far away was something I really built in yesterday when I was talking about the stationary phase. It was very important there that it took R very, very big. So you can think that, this, I'm essentially in some region where I'm taking R effectively to infinity. Maybe it's not quite infinity. Obviously, we have in mind an application where we have some LIGO and some event very, very far away. But they are, like, the distances are really sufficiently far that at least there's some sort of an idealization. I want to think of that R as being close to infinity somehow, if you want. There's some little delicate issues about that. Not really going to affect us today, I don't think. But yeah, so just think of this R as being very, very large. So the diffeomorphisms, changes of coordinates of our space-time, which do not fall off. So, well, these are called, these things are called large gauge transformations or large diffeomorphisms. So just large gauge transformations. Now another maybe qualifications, I'm really interested in space-times which at large distances asymptotically look like Minkowski space. So these are the asymptotically flat space-times. Asymptotically Minkowski. So the curvature, somehow in the middle of space-time can be whatever it wants. It can be large, but so long as very large distances, the space-time looks like Minkowski space, well, then we're good to go. Okay, so you can always find coordinates. So the line element. The line element at large distances takes this form, the Bondi form. So this is ds squared. So there's so we work in essentially retarded coordinates. So you want to think of this U. I mean, these are supposed to be, it's a curved space, but this U is somehow a version, if you want, of the retarded time. But there are other possible terms in the metric, du dr. So I'm going to have angles theta a. A goes from 1 to 2. Minus, this is just a mostly minus signature thing. So big omega is going to be just the round metric on the two-sphere. Now, yeah, so this is the round metric of the two-sphere. So omega AB d theta A d theta B will be, d theta squared plus sine squared theta d phi squared. CAB here is the first correction to this round sphere metric. It has a name. People call this CAB the shear. Maybe the Bondi shear. So it's traceless. There could be other terms here. So these dot, dot, dots are other terms that are falling off as higher powers of distance, 1 over r squared, etc., which we're not really going to care about. The reason they're not really going to care about this is I want to discuss how this metric relates to this expression here. And this expression here manifestly has a 1 over r. In our scattering amplitudes methods, we're only computing the 1 over r terms. There can be 1 over r squares, but this computation is set up with the notion that we're not sensitive to them. We're just computing the 1 over r term. So the plus dot 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 won't play any role in our discussion. Now, one thing to note about this metric is basically its defining property, at least the defining property as far as I'm thinking about it at the moment, is that there's no GRR and there's no GRA. These are three metric terms that are set to 0. Now, you could say more about the structure of these GUUs and GURs and GUAs. They're not going to be important for us, so I'm not going to say more about them. There is more things, there's a lot more that can be said about this, but we're not going to need too much about it. Okay, now it's this thing here. The shear is the thing that I'm really going to care about. One way to understand it is that the shear is essentially the transverse traceless part of the metric in this Bondi gauge. And that it's transverse because it just depends on the angle. It's transverse to the sphere. There's some sphere here, and this is some big sphere. It's more or less a round sphere, but it has some fluctuations on it. So the modes of the metric that are transverse to the sphere are the ones that we associate with gravitational waves. So they're inside this CAB. So you just think of it as a transverse traceless part of the metric. These other things here are somehow, Coulomb terms, if you want, non-radiative terms. Well, I'm working in 4 dimensions, so this is a 2-sphere. Okay. Now, so you can always put asymptotically flat spacetimes into this form, put the metric into this form, but there are still diffeomorphisms. This doesn't completely fix all of these functions. So there's a group of symmetries of the spacetimes at large distances, which have the property that they map this Bondi form of the metric onto the Bondi form of the metric, just mixing up the various terms like the CABs and the various Gs. Right? So the group of symmetries, the group of asymptotic group of diffeomorphisms which preserve this form are known as the BMS, group. So it should be large diffeomorphisms. I mean, there's fine print about this Bondi form, about these the structure of these Gs, which are also relevant for the definition of this group. Anyway, this diffeomorphisms. Yeah. I have to make a sentence out of what I've just written. Diffeomorphisms preserve the Bondi form. Yeah. Well, the trouble is, I want to use form twice. Bondi metric. So this BMS group, BMS stands for Bondi, Metzner, and Sachs. But there was another person famously who is not included in the name. It's really Bondi, van der Berg, Metzner, and Sachs. But anyway, for van der Berg. Okay. Now, one way you can think about this group, a naive way to think about this group, is it includes basically just plain old space-time translations and rotations. So the Poincaré group. But it's augmented by a specific and interesting infinite dimensional set of transformations, which are known as super translations. So I think super translations is a terrible name. I'm going to say so-called super translations. Well, particle physicists, when you start talking about super anything, they immediately begin to think about supersymmetry, which is not observed in nature. Anyway, but this has nothing to do with that. So these super translations are they're changes of this u coordinate by a function of theta and phi. So That's to say that there are angle-dependent shifts of the origin of proper time. So we have a big sphere. Think of maybe many different observers on a big sphere, and you just change the proper time origin for all of those different observers in a big sphere. This preserves this boundary form, but the terms shift around. Now I'm going to write this as u plus t of n, right, where n is the vector over here. This vector here, right? This vector n just depends on, it's the vector that points at the various observers, so it has the thetas and the phis in it. So we can package up all the thetas and phis into this n. I mean, the n is literally going to be like sine theta cos phi, sine theta sine phi, and cos theta, with the 1, the time component. So I can package up all of my angular dependence in the n, and that's going to be the useful way for me to do this, because I'll be able then to derive formulae that look like the one that will match the formula on the left. Okay, now under a super translation, so these functions here, they don't, well, that stays the same, but these functions shift around, and in particular, the shear transforms us. This transformation. So the shear picks up a transformation. Shear transforms as delta CAB is, so there's a u derivative on CAB times t of n plus another term. Where the d here, big D, is a covariant derivative on the sphere. This function t is a function evaluated on the sphere, and the shear is transverse to the sphere, so there's some projector going on here. So the relevant derivatives that appear are the covariant derivatives. Okay, now the observables that I've been talking about, I mean, obviously this h mu nu on the far left there is some gauge-dependent thing, but even if I were to compute something, I mean, as I said yesterday, you might think, you don't like this gauge dependence, maybe I should compute the Riemann tensor, the expectation value of the Riemann tensor, and extract out of that the psi4. But still, there's, the psi4 shifts under a BMS transformation, or these super transformations. So if you have psi4, or like the dominant term, the 1 over r part of psi4, the thing about the psi4 is it's a function of time. I mean, think about gravitational wave. I mean, it's a function of time. We read it off as a function of time. Time is a coordinate here. It's precisely this coordinate that picks up a super translation. So this psi4 will shift to psi4 of u plus t of n. So no matter what we do, even if I was talking about the psi4, I'd have to face this issue that there are some gauge dependence of the quantities I'm computing. So that's why, well, that's one reason why, rather than computing psi4, which is what we actually did in our earlier papers, in these lectures, I've been focusing on the computation of h. Ultimately, computing psi4 doesn't really buy you a tremendous amount. Okay, very good. So now, here, I was comparing the Donder gauge, h mu nu, to these expectation values we've computed in quantum fields. But when you understand that the H mu themselves, the classical guys are going to pick up these kinds of BMS transformations. Well, then, clearly it's not necessarily particularly relevant to pick one of them, to pick, say, this Dodonder guy and compare it directly to that, to this quantum field theory, and say, well, look, they don't agree, so everything is, nothing makes sense. It's too fast. We would need to decide, which gauge this computation, which BMS gauge this computation was set up in, to compare it to an appropriate metric deviation in the same gauge classic. So it doesn't look like Dodonder is working, but I have a whole BMS group's worth. It's an infinite dimensional group's worth of gauge equivalent HBNUs, which I can compare to that. So we should try and line up the computation so that we understand what BMS frame, people talk about the frame for the choice of this large gauge transformation. What BMS frame should I use to compare classical computations to quantum field theory computations? Yeah. Yeah. Well, they're all related because, part of the reason why there is a relationship like this is that these BMS transformations are relevant at very large distances. So very large distance in Fourier space is very soft wavelength, very low frequency. So these issues of super translations are going to connect to soft aspects of waveforms. So, for example, to the memory. You'll see that connection becoming a little bit more apparent in these lectures. I'm not going to completely go to this infrared triangle stuff, but you'll see some of the reasons why soft physics in particular is directly relevant. Yes. Yeah. I mean, the transformation of psi4 is the most mild. The other Newman-Penrose scalars pick up. So indeed. So I mean, if you're a Newman-Penrose person, I'm really talking about the 1/r part of psi4. Okay, now very good. So I also want to spend a little bit of time understanding a little bit better what we actually mean by these formulae over here. In particular, I want to show you that how this shear, the CAB, connects to these computations here. Okay, now when I set up the perturbative graviton field a couple of lectures ago, we just had two creation and annihilation operators. We had two helicity states. The quantum field. So two, let's say, two ladder operators. By which I mean the a plus or minus 2 of k for each mode. Now that's relevant because these are the only two sort of fluctuating degrees of freedom. We set up quantum field theory, we're talking about the radiative modes. There's some story that the states transform under helicity, under a little group, and therefore there's only some allowed set of states. These states carry energy and momentum to infinity. So there's only two modes in the quantum field for each momentum k. So we don't really expect to capture the full classical metric. I mean, the full classical metric, the full HBNU is 10 components, right? Here I only have two things that I'm playing with. So I'm never really supposed to be set up to calculate to extract the full h mu nu. So the expectation value, so I wouldn't really ever expect this h mu nu psi. Classical. And functions. In other words, the quantum field is set up to compute the transverse traceless modes. So really, the thing that we should be comparing to is not the full h mu nu, like I compared to here. I should really be comparing to the shear, the CAB, associated with that h mu. The transverse traceless fluctuations in the h mu, not the whole thing. So in a way, the notation h mu nu is a little bit of a, it's not really quite the right notation. If we called it, I had to call the operator C mu nu or something like that to begin with, it's called a shear operator. That would actually be a more reasonable name for it. Anyway, I want to show you that this is the case rather than just assert it. So in order to show that this is the case, I'm going to pick, pick some notation that makes the calculation simple. Yeah. Okay, so the first thing I'm going to do is just pick some coordinates from my observer, which are adapted to, well, to this sort of Bondi story, but are also related to the stationary phase computations, which led to this expression in the quantum field. So the coordinates I'll choose, so coordinates for our observer. They adapted to the stationary phase. So I'll let my observer so I'm going to give my observer some proper velocity. I'm going to call it big U. Now, we had this vector n from before. So n mu is 1 comma n hat. So this was set up in the coordinates of the observer, right? Basically in this frame where the observer has some proper velocity. The rest frame of the observer, this is the expression for n. So n dot u is 1. It's just that one. This u in this frame would be 1 and zeros. Then you have this dot product. And obviously, n squared is equal to 0. So we'll write the coordinates as x mu equals some coefficient little u, u mu, plus the radial distance r n mu. Now, in the rest frame of the observer, this would look like u plus r, because in the rest frame of the observer, u is 1, 0, 0, 0, n is 1 comma n hash. So you'd have a u plus r in the 0 component. On the spatial components, you'll have r n vector n hash. And this makes sense because u plus r should be the time. Right? The retarded time u is t minus r. Here it is. U is t minus r. So you'd expect then that the time component should be u plus r, then u plus. So this choice of coordinates here has the property that the little u is built in. the distance is built in on this vector n, which was important over there, is also built in. So it's a nice set of coordinates for us to work with. Okay, now those are the coordinates, but because when we're talking about these metrics, it's useful to form h mu nu, dx mu, dx nu. I'm going to compute d of these coordinates. So dx mu will be a u mu du plus n mu dr plus r dn mu. Those are the angular guys. There's two angles, the theta's in here, so I could rewrite this as u mu du plus n mu dr plus r dA n mu d theta n. Now, we had the fact that n dot u is 1 and n squared equals 0. So n squared equals 0 is going to imply that n dot dn 0. N dot u is 1. Tells me that u dot dn is equal to 0. So there's various dot products here, which simplify life. By the way, I mean, this dot product here is Minkowski spaced. Okay, so the flat space line element is useful to write that out because we'll be able to understand these DANs a little bit better. So I'll call that ds0 squared, dx dot dx. Okay, so it'll be a u mu du plus n mu dr plus r dn mu e to mu nu u nu dr u nu du plus n dr plus r dn mu. Okay, so performing the dot products here, u squares to 1 because it's a proper velocity. So there's going to be a term du squared. U dot n is 1, so there's going to be two terms du dr. Now dn has 0 dot product with u and with n. So the only way I can get something out of the n term is just to multiply it by itself. So r squared plus dn dot dn. Okay, well, this is you can see why I like these coordinates. The flat space part is taking Bond form, at least for the du's and drs. Now these terms here in flat space, these are just ways of writing dt squared minus dr squared. There's this relationship that u is t minus r. So if you just switch to t rather than u, you'll find you get the normal dt squared minus dr squared out of this. So this term here then is the metric on the two-sphere. So this is equal to minus because of the mostly minus metric. So these DANs then dot together to give you the metric on the two-sphere. Ooh, okay, so this dn here, I can write it as dan mu d theta a, dan mu d theta b. So this term here is going to give me this omega a. Okay, so this n vector is it's a nice thing. I mean, it's a very familiar thing, really. It's just sine theta cos phi sine theta, sine phi, cos theta, so 1. Okay. So that was, let me see. So I started out saying that I was going to make 2 choices. So this was the first choice. So I picked some nice coordinates for my observer. The second thing I'm going to do is I'm going to change the gauge for the polarization vectors I've been using so far. So we had for our polarization vectors epsilon h of n dot n is equal to 0. Now, that's always the choice we make with these polarization vectors. They're always sort of in this Lorentz type gauge. But we also chose, we picked a gauge where epsilon dot zeta was equal to 0 for some zeta, which is a light-like polarization vector. Sorry, a light-like object, zeta squared is equal to 0. So this was our gauge choice. Now, given that I have this observer and I picked some nice coordinates for my observer, I'm going to choose a different gauge which is associated with the observer. So I'm going to change the gauge. So that means I'm going to have different polarizations, epsilon h of n, which are epsilon h, the old ones, plus some x times n mu. Now, remember, n really started, like the momentum of these, I have in mind gravitons here. So the momentum of the gravitons were omega times n. But the omega doesn't matter here. I mean, here you can see this, maybe I should have written this as epsilon of k dot k, but that just involves a factor of omega, which cancels out. So I'm labeling them by the direction n instead of by k. Similarly here, there's no omega dependence that we have to worry about. And here, well, maybe this started out as being a k, but then that just reabsorbs. I've absorbed that omega into x. Okay, so the gauge I'm going to pick is u of epsilon prime h. Now that's always possible because if we start out with a gauge where u dot epsilon is non-zero, like this gauge, well then I want u dot epsilon prime to be 0. So let me dot this equation by u. I'll get the non-zero term from u dot epsilon. I'll get plus x times u dot n. U dot n is 1. So x will be just minus the epsilon dot u. So I can always find an x that puts me into this gauge. Okay, so, and then I'll drop the prime. So I'm just going to assume now that we have this choice. Oh, good. This has to go away. So the important thing to remember about this Bondi choice is just that the shear is the d theta A, d theta part, theta A, d theta B part of the line element. Now, regarding the polarization vectors, I want to make one more remark. So the completeness relation. Because we've changed the gauge, the completeness relation changes. And the major difference between this gauge choice was that zeta squared was 0, but in this gauge choice, u squared is 1. And because of that difference, the completeness relation takes a slightly different form. Completeness relation is e to mu nu minus nu u mu times nu mu plus n mu. This is easily checked. So the completeness relation before had, this term and these terms were similar. There was a denominator downstairs. It was k dot zeta. So in a sense, there's a denominator downstairs here as well. It's n dot u. But since n dot u is 1, don't need to write it. But this term here is nu, and this term is necessary when you have a gauge choice that doesn't square to 0. So it's easy to check this. You check it in the same way as we checked the completeness relation a few days ago. Just take a dot product out on your basis of vectors. And then you'll see the left-hand side is the right-hand side, then it's right. So one quick way of seeing that you need this extra term is just to dot it with the big U. Dot this with big U on the left, I should get 0. I dot this with say u mu, there's a u mu from here. Here, if I dot it with a u mu, n dot u is 1. This term will subtract, so I'll get 0 from these two terms. I'm dotting in by n, as there by u. This u mu times the u I'm dotting in by will be a 1. So there's a term that I have to worry about. So this term appears, it didn't appear before. So I need to subtract it. If I dot in with my big U against this term here, I'll get 1 from the first n, and then this n cancels. So that's why it's okay, yeah. Now, so what this projector actually has a nice physical meaning. So since u mu is, well, in the observer rest frame, u mu takes this form, and mu takes this form. Then any vector which has got some components in, say, in the time component gets projected away because I can write the time component as being some amount of u. So the u, the time component, gets projected away from this projector. So we can forget about the one here. What's left in the n mu is just the normal direction to the sphere. So also all directions that are normal to the sphere get projected away. And all this, what this projector is really doing is it's projecting an arbitrary vector onto this part that's tangent to the two sphere. So this thing projects you onto the tangent space of the two sphere. That'll be helpful to us in a little while. Okay, very good. So I finally finished picking these choices that I wanted to make here that will allow me to line up the expressions that we computed, the one on the far left, for h mu nu with the shear. So so what we just have to do, the basic step is just to compute the operator h mu nu after stationary phase and dot it with dx mu dx nu. We'll take this operator h mu nu. Okay, probably need to put a space for this. Very good. So the operator after stationary phase has this form. Come on, Felicities. Now, the polarization vectors here these guys here, they're not dependent on the frequency, so I can basically pull them out of the integral. I'll have, well, that guy was the expectation value. The full operator, I'm going to have its creation and annihilation operators. Times epsilon nu h of n, epsilon h nu of n. Now I want to write, well, there's a plus CC term, complex conjugate. I'll add that at the end. So I'll dot in by these dx mu's and dx nu's. I still have them. So the dx mu has these three terms here. So one of the terms involves a big U. Now we've just chosen the gauge that U dot epsilon is 0, U dot polarization vector is 0. So I don't have to worry about this term in dotting dx into h mu nu. The other term has this n. Now n dot epsilon is always 0. So I don't have to worry about this term when I'm dotting dx into h mu nu. Just dump it. This term I do need to worry about. It's there, right? There is some term, there's no reason why epsilon dot dn is 0. Indeed, really, they're kind of closely connected. In our gauge, these epsilons are basically just vectors on the two-sphere. That's why the projector is a projector onto the two-sphere. And these dn's, we know that they're closely connected to, I mean, they can also form a basis on the two-sphere. After all, they dot together to give you omega AB. So these things aren't 0. Definitely not going to dot together to give you 0. So we have to worry about those terms. There will be, now dn, that comes with an r squared because there's two terms, two r dn's. I can write them then as dA n mu, that's dotting into that guy, dB n mu, d theta A, d theta B, plus complex conjugate, to take complex conjugate to the whole thing. Okay, now the point of this is this part, whatever state, I mean, I want to take an expectation value of this on some kind of state in the end of the day, right? But whatever I do, no matter what state I'm working with, I was only ever going to get the shear, the CAB, right? The CAB is the coefficient of d theta A, d theta B. It had in the metric, it had 1 r. This cancels, this indeed has 1 r. I mean, that's just normalization. Anyway, so this thing here is directly the shear. So I could write this as maybe write it in a suggested way like this. So okay, so I mean, a summary of this story so far is, although we write expressions involving, graviton quantum fields, and maybe might naively think that that its expectation value should be the classical h mu nu. That's not really the case. You're only ever going to be computing the angular parts of the quantum field. It's exactly the same in electromagnetism. The expectation value of a mu operator isn't the full classical a mu, it's the angular part of a mu. And that is built in from the start when we say, oh, there's two polarizations of a photon. Obviously, there's 4 functions in the classical a mu. You're never going to get those 4 functions. You get 2 of them, the ones that carry energy and momentum out to infinity. That's what the photons are doing for you. It's the same with the gravitons. They carry energy and momentum out to infinity. That's captured in the classical treatment by the shear. And the quantum formalism just directly accesses the shear. It doesn't give you the rest of the metric. So when I compare then, so this puzzle at the start, that it seems a bit weird that the initial expectation value of the h mu nu is 0, when you have non-zero de Donder perturbations. Well, you shouldn't look at the full perturbation. You should only look at the shear that's in the perturbation, not the full thing. So a fair comparison of quantum field theory and classical field theory is a comparison at the level of the shear. Okay, so some comments, some more comments. Now, the shear of Schwarzschild in its rest frame is always 0. The classical shear. So I'm thinking of the classical Schwarzschild metric. That's true because of spherical symmetry. This by spherical symmetry, the angular part of the metric, you're always going to choose it to be just r squared omega ab. Never going to have a CAB overall. This is true. It's true in the rest frame of the Schwarzschild, but that's not really what we're interested in. I'm interested in taking two black holes and shooting them at one another. So I'm not in the rest frame. Maybe I'm in the CM frame or something like that. And when you boost them, if I take a black hole and I boost it to some velocity, so I have some observer at rest and the black hole is moving with respect to that observer, and I look at the shear in that observer's frame, it's not 0 in general. So we're interested in a boosted black hole. So there'll be some V mu, which is gamma V, gamma. Gamma beta. So then the shear is in general not 0. So you can go ahead and compute. I didn't ask you to do this in the problem set, but you can go ahead and compute the shear of the de Donders gauge perturbation with velocity v, and you'll find it's not 0. There's some little bit of work to put it into Bondi form. So in this sense, there is still a puzzle, if you want. I've been saying, well, look, there's a bit of a puzzle comparing the quantum field theory to the classical field theory. But certainly, if you compare the quantum field theory to classical field theory into de Donders gauge, well, then the shear doesn't match. But now I did give you an exercise, which is interesting in this respect. So you could take the Schwarzschild metric in another set of coordinates. And a very interesting set of coordinates are the Kerr-Schild coordinates. So the Kerr-Schild coordinates are a large gauge transformation of the de Donders coordinates. Okay, well, I mean, there's more than one obviously large gauge transformation, but this is an interesting one. So the exercise, the tutorial, is to show that if you take a boosted Kerr-Schild Schwarzschild, you take that line element, expand at large distances, you'll find that it takes the Bondi form. So there'll be this du squared, the du dr, etc. But you'll find, so it's in Bondi form to quite high order in 1 over r. So we're doing expansion in 1 over, powers of 1 over r. We're really only interested in the dominant corrections in 1 over r. If you expand high enough in 1 over r, going into subdominant terms, I think it's 1 over r cubed, it stops being in Bondi form. But it's in Bondi form to quite a high order, and in particular to the order that we care about. So let's say it's in Bondi form to sufficient accuracy. and it has the property that the shear is 0. So this is the form, the classical metric that matches the computations in quantum field theory. So the quantum field theory, is set up essentially to do perturbation theory around the Kerr-Schuld form of the metric, not the de Donders form of the metric. That's just the way it works out. So you finally, if you do this exercise, you'll finally have a match between the classical setup and the quantum setup. So, I mean, this then, if you want, is the frame. So there is a large gauge transformation between the Kerr-Schuld form and the de Donders gauge form, and that is an interesting large gauge transformation. And it's interesting, it's also very relevant for us, because when you're doing these computations, these post-Minkowskian computations, it's very good to have something to compare against. So I said yesterday that the next to the leading order waveform had been computed using the scattering amplitudes methods and compared to computations that were performed classically in the NPM-PN, like the matched post-Minkowskian post-Newtonian multipolar post-Minkowskian. So the comparison between NPM PN computations. This comparison required a large gauge transformation to be taken into account, because these computations were done, I mean, it wasn't understood at the time, but these computations were implicitly done in this frame. The NPM-PN computations were done in a frame equivalent to the de Donders gauge. So the comparison required taking a super translation into account. Right, so, well, I mean, it's an issue that appears very commonly in gravitational waveform studies, that if you do some sort of a computation, you have to say what Bondi frame you're in, because you want to compare it to somebody else's computation. And if they've chosen a different Bondi frame, the psi4 will be different, right? Because the psi4 depends on the choice of the t, and the t is the thing that maps you between Bondi frames. So you're not going to get the same answer unless you're comparing the same thing. So all of this story, the super translations, etc., was relevant, was pragmatically relevant here, because when the comparison was initially done, they didn't agree. But then it was realized that they didn't agree because they were performed in these different frames, and once you took that into account, they did agree. So this is one of the reasons, pragmatic reason why we actually care about this story here. It's not just because it seems a little bit puzzling at first when you take the expectation value of the H mu and you get 0, and you think, oh, well, that seems a bit funny. It's not just for that. In the end of the day, there's actually a pragmatic reason to care about this, right? Of course, it does resolve this thing seeming a little bit funny. It's not so funny. It matches perfectly. It's just in a particular choice of asymptotic frame. Okay, so now, what I want to do in the remaining time is to show you that if you want to perform a quantum field theory calculation in a different Bondi frame, that's perfectly possible. And in a way, it'll substantiate this claim here. So I'm claiming, that essentially I've got one data point. I have computed, this initial metric expectation value. It was 0. I have done another computation where I rooted around for various different expressions for the Schwarzschild black hole. I boosted them, and I realized, aha, one of them has the property that its shear is 0. So therefore, therefore it's right. That is one match. It would be very good to see that that if I can manipulate my quantum field theory such that I can be in an arbitrary Bondi frame, well then the transformations should be the transformation, the delta C that you would get from transforming from this frame where CAB is 0 to some other frames. So we should get the transformation of the shear under a super translation from quantum field theories. So then we will see that if you start with this frame, this Kerr-Schild frame, and we perform a super translation, we will end up in whatever frame we want to be in, and there is a detailed match in every frame, not just in one frame. So I'll finish. So I'll describe. Say the amplitudes computation. Okay, so what this basically means is that I want to be in a situation where when I take my the expectation value over here of the h mu nu, that it isn't 0. And the idea, it's an idea that already came up last time. I observed that this h mu nu is 0 because the annihilation operator here for gravitons was acting on a state that didn't have any gravitons in it. So then obviously that annihilation operator was going to annihilate the state. It's only not going to annihilate the state if there are some gravitons in it. So in order to shift this around so that I have some expectation value in the far past, I'll do the obvious thing, which is to put some gravitons in my initial state. So now I still want to put gravitons in some way that is classically sensible, because I want to make connections to classical physics. So I'm not just going to put in one or two quantum gravitons. I have to put in something that has the property that it makes sense classically. So this brings me to the topic of coherent states in quantum field theory. Okay, so coherent states are just, you might have come across them before. There are particular kinds of states which you can make, which have nice properties. So coherent state alpha, I'm going to be interested in coherent states of gravitons. So the coherent states are always defined to be eigenvalues or eigenstates of the annihilation operator. So now our annihilation operator in gravity has these helicity indices. Let me just talk about a momentum k. So if we act with the annihilation operator on this state alpha, now I'm writing alpha here as an abbreviation. It's really going to be an alpha that has helicity indices and depends on some momentum. So and the definition is this. So when we attack the state with the annihilation operator, we pull out exactly the parameter of the state. So this alpha is really alpha HH, and there's some momentum dependence. Now it's convenient for me, this is not conventional, but it's convenient in this discussion just to shove an I here. So the conventional definition doesn't have the I there. I could put an I here, and that would be conventional, but it just looks weird. So I'm just going to put that in. You'll see why in a moment. It's not big deal. We also normalize these coherent states to unity. Okay, very good. Now, you can show that. not that well. So these coherent states take the form. So you can always write this alpha in this form here. So it's an exponential of a sum on helicity, an integral over momenta. Yes, and there's my I. So it's convenient for me to factor out an I here so that everything else I'm going to write is Hermitian, and this I is directly that I there. Yeah. So we have alpha HH, okay, a dagger HH, plus complex conjugate, we write it alpha star, I think that's HH. Okay. So coherent states always take this. At least this is one way you can write them. I put a little exercise in the problem set to manipulate some coherent states in case you haven't seen them before. So I simplified the problem in the exercise by, rather than having a quantum field theory, I just took a case like a simple harmonic oscillator situation where you just have one creation and annihilation operator. It keeps the formulae very simple, but structurally they're more or less identical. So I think you'll, once you see how it works for the simple harmonic oscillator case, then this will be, obvious how this works. It's just slightly more complicated with various sums and integrals and so forth. Anyway, now the significance of these coherent states is just that when you take the expectation value of your field operator, so let's take the expectation value of h mu nu. So let me write it out in the stationary phase form version. So there'll be a minus I over 4 pi r, summon integral from 0 to infinity. So polarization vectors. Okay, so then we will encounter the expectation value of the annihilation operator in the next step, right? But the expectation value of that annihilation operator, because alpha is a coherent state, the expectation value, so the annihilation operator acting on alpha just brings out this I alpha, and then the bra will hit the alpha and give you 1. So we'll pick up this I. And this I very helpfully cancels that minus I. And we have alpha HH of, well, K, but now K is omega n, e to the minus I omega u, plus complex n. So you see what's happened here is we've replaced the operator A with a function alpha. That's essentially why coherent states are useful. So when you take the operator quantum field, you take its expectation value on a coherent state, you'll just get a classical field with an arbitrary function in here. Okay, so the basic idea then is to use a coherent state of gravitons, to dress. People speak about, so our initial state psi over here, some kind of a state of just 2 bare particles if you want, and then we speak about dressing this state with a bunch of gravitons, like a coherent state of gravitons. And I'm going to choose this graviton dressing parameterized by this function alpha to recover the shear of an arbitrary metric perturbation. Okay. Okay. Now, when I said arbitrary, I'm really interested in metric perturbations of, in the far past. So the metric perturbations I'm thinking about are the linearized metric perturbation of a Schwarzschild black hole. Talking about Schwarzschild here. So now those things are time independent. It's the the linearized metric in the far path was before there's any scattering, you just put in the solution for an isolated black hole. So that thing is time independent. There is time dependence here. It's right there. So what we'll do is choose the coherent dressing, this alpha here. I'm going to choose it so that it's got a delta function in frequency. And that delta function in frequency will get rid of the time dependence here. So I'll get something that's static. This is now beginning to connect to soft physics. So you should think of this dressing as really being some soft dressing. So I'm going to choose alpha, omega. Well, maybe I'll separate them to include. Resulting shear. It's static. I mean, there's another reason why you might want to do this, and it gets back to the definition of the particles here. So let me write a little bit of notation. I'm just going to focus on single particle states now. You know, I have in mind, as I said before, that the final, the application of this will have two black holes, but they're just linear combinations. So I'll focus on just one. So I want a state for like a point-like particle now, a single particle state. So I'm going to call it psi1, just to differentiate it from the psi over there, which was a two-particle state. So it's an integral d phi of p, some wave packet for the phi, and now some particle p. There's no point in putting an impact parameter in. I'm like, good, I would move my origin, but there's no point, so I'm lining up my particle being along the origin here. So this is a massive particle, one of the H's, made with the creation operator for a massive scalar particle, put into a wave packet to localize it in position and momentum space, and then integrate it over d phi p. So this is the thing I want to dress with a bunch of gravitons to give me the shear in a different frame. Now, this thing has some, the state here, the state P has some mass, some energy and momentum, some mass. When I dress it with some gravitons, I don't want to mess with the amount of mass I've already put in here. So you want this, this dressing factor to not contribute to the energy and momentum of this particle. So this is another reason for just putting in this factor delta of omega here. You should really think about this as not being a delta function at zero frequency, but it's small. So it's really just some distribution, but the frequencies of these gravitons is very small compared to the momentum of the particle itself. And I'm idealizing that as being a delta function in much the same way as we idealize this distance between the observer and the source as being so large that it's basically infinite. So the very largeness of that distance is directly related to treating this as being this very small thing as being just a delta function at zero. Not really zero frequency gravitons, they're just low frequency gravitons. Okay, so I'm going to attach a coherent state of gravitons with this. And I'm going to define, so basically this thing here, this operator here, I'm going to define it as, I'm going to give it a name and call it QS. It's like a dressing operator. So I want to pick a particular value for alpha. I'm going to put in the delta of omega for the reasons I just said. Then I'm going to attach the rest of the alpha. Now this alpha has to have helicity 2, helicity weight 2. In this context, these things are usually called spin weight. So this alpha is really a spin weight 2 function. You might well be familiar with spin weighted functions. In this the setup, I can generate spin-weighted functions by differentiating a scalar function twice and attaching a vector that carries the spin weighting. So that the vector I have at my disposal are the polarization vectors. So what I can write here is, now I have to get the helicity index down. That means epsilon star. what indices, mu. Then I have two derivatives, and what's left is just a scalar function of angles. What's complex feature? So this is my parameter. It's a scalar function of angles. So I'm going to choose it to be real. In principle, it can be complex, but it's enough for our applications to choose it to be real. So now, choosing this to be complex, this would be the most general dressing, which has spin weight 2 and has, it's soft, has low frequencies. So it's the most general coherent dressing. Okay. So we'll dress it with a coherent state of gravitons. So I will replace the psi1 by e to the I qs. I like to indicate that it's a function of t. I'm writing the function of t in square brackets because we're integrating over t, so it's really a functional of t. And this operator here is the dressing operator. So this is attaching onto our massive particle a cloud of gravitons. So the last computation then is to take the expectation value of h mu nu on this dressed state. This section little title. You get super translations from dressings. Okay, so we just have to compute the expectation value of this dress state, e to the minus I qs of t, on h mu nu x, e to the I qs of t, on psi1. Okay, I'm going to use the version of the h after stationary phase. So we'll have minus I over 4 pi r. The sum on helicities, integral d hat omega. Polarization vectors. And okay, so and then the dressing factor. Well, the dressing factor brings down an I, a delta of omega. These polarization vectors. Two derivatives. Plus the Hermitian conjugate. So the I goes away. I can do the integral over omega with this delta of omega. So that goes away. There was an e to the minus I omega u, which I've dropped, but actually doesn't really matter. Back in. That goes away when we do the integral over omega. When you're integrating over a delta function with half weight, there's a factor of 2. But there's 2 terms here, and they're going to contribute equally, so the factor of 2 goes away. So we will get 1 over 4 pi r, sum on helicity. polarization vectors. Two derivatives of t. Okay, we performed the polarization sum. Now, the polarization sum, as usual, has these three terms. It's a graviton polarization sum, so each term is quadratic in the projector P. It's the projector now with the additional term. But two of the terms are going to give the same value because you're symmetrizing on rho and sigma. So we will get 1 over 4 pi r. 2 e u rho p nu sigma minus p mu nu p rho sigma rho d sigma t. Okay, now it's actually nicer to again, just to extract the shear, to multiply in by dx nu. So let me instead just tack on the two dx's. So the two dx's, the only part of it I would care about is the terms which are r dn. So there's going to be 2 powers of r. We'll get the r upstairs over 4 pi. Let me write it as d theta a, theta b. So then we'll have dA n mu, dB n mu, times this projector. Sigma, 0. Okay, now the projector, as I said before, what it does is it projects onto the tangent space of the sphere. So it's projecting these derivatives onto the tangent space of the sphere, right? So you do a derivative, you project it onto the tangent space of the sphere. That's what a covariant derivative is. So this projector projects these derivatives onto the covariant derivative to the, on the two sphere. These are just change of basis matrices onto the angular directions on the sphere. So this whole thing is r over 4 pi d theta a d theta b times 2 dA dB minus omega ab b squared theta. And this combination here, well, up to the 4 pi, is the BMS, like a super translation. It's a super translation in the case where the initial shear is 0. So the general super translation had 3 terms. There was a term which was du of CAB. So in our case, that term is 0. The remaining 2 terms in the general super translation of a shear are these terms here. So you see that by dressing the particle with this T of n, you can organize the computation to be in whatever BMS frame you want, including, if you wanted to be, into Donder gauge. Now, in practical calculations, if you're using this formalism, there's no need to do this. Right? This computation just assures you that the formalism makes sense, that we can access whatever Bondi frame you want, and it substantiates the claim that I made a little earlier. You're going to do this exercise to see that the shear of the Kerr-Schild form of boosted Schwarzschild is 0. Well, if we start in that frame and we do a classical BMS transformation, you would end up in precisely this frame here. And that is achieved in the quantum field theory by this dressing. So it substantiates the claim that the quantum field theory is set up in the frame where corresponding to the Kerr-Schild coordinates, which appear also in amplitudes in seemingly unrelated ways. It's kind of an interesting thing. Okay, that's all I wanted to say. Thank you.
So I had a question. So can you actually explain the first step of this calculation?
First step here. So this is so what I did here was just I used the coherent state. So the annihilation operator acts on so this e to the IQ S of t stuff here. This e to the IQ S of t here is making a coherent state, and the parameter of the coherent state is this alpha. So we can read it off from this QS. Has this delta of omega, has this epsilon, and the derivatives. So what I did here was I replaced the expectation value of A by the delta, the epsilon, and the derivatives.
So why doesn't the QS have any operator?
Oh, it doesn't have an operator. It's because I left out the operator. That's your right. Thank you. Yeah, it doesn't make any sense. So A dagger HH of K. Thank you. Important correction. Yep. Well, because my gravitons, I'm putting them in with essentially zero energy and momentum. They don't contribute to the energy and momentum of my initial state. So I don't think the Goldilocks inequalities change at all. Actually, I think they stay exactly the same. It would be different if these started to contribute substantially to the, But the picture here is always that in the far past, the gravitons that are coming in, that are in this dressing are very low energy. Yeah, but still classically meaningful, so that there's still an expectation value.
So the factor of R in the numerator, that's not going to cause any problem at large distance.
The factor of R in the numerator, but I must say I find it ugly. It's sort of standard to write it in this way. But now the reason why there's a factor R in the numerator is just because the d theta a is not normalized. So if I used a frame, if I normalized these to be unit covectors, then I would absorb a 1 over R downstairs for each d theta a, and this would fall off like 1 over R. Right? So it's just a normalization of d theta. So if you used a frame basis on it, it is just a 1 over R factor. You'd see this thing falling off like 1 over R everywhere. I think it's nicer. Personally, I like to set Bondi up that way myself because then it's completely obvious that everything is just at order 1 over R. Anyway, it's somehow not standard to me.
Okay. So this also marks the end of our first course this week. I hope we all learned a lot. I know I did. So please join me in thanking Professor Donal O'Connell once again for taking out the time to come here and deliver this course. We hope to see you again at ICTS soon.